Alright, in last video we went over integration factors in a quick little example, but in this video we're going to go over a applied example which is very likely to be on your final. This question is very common on any exam or quizzes, so it's good to study up on this. After that, we're going to take a break from integration factors and we're going to go into Unit 2, which is second order derivatives. But for right now, I want us to look at our question, which is a tank contains 100 liters of pure water. A solution with concentration of 4 grams a liter is pumped in at a rate of 5 liters a minute. The mixture is pumped out at 4 liters a minute. What is the concentration as it gets pumped out? And then what is a function x of t where the amount of salt in the tank at time t? Can we find a function that represents that? And if so, what is it? Well, first, we're going to go over some variables and some basic equations that apply to a problem of this type. So first, x of t is just the overall amount of salt in the tank at time t. V of t will be defined as the volume of the liquid in the tank at time t. So for example, we start with 100 liters of pure water. So at time t equals 0, V of t equals 100. And note that it says pure water, so its initial concentration would be 0. Now we have Ri, Ro, Ci, Co. Ri is the rate in. At what rate, how fast is water being pumped in? And this water may have like sugar or salt in it. It can have a concentration, or it may not. Ro is what's being pumped out. And note that when you have a tank and you pump something in, Ri times Ci, because it might have a concentration, it's going to go in, be stirred up, and then it's going to be pumped out, which is Ro times Co, the rate out times the concentration out. So that's basically what this problem is. We're pumping stuff in, we mix it up, and then we pump it out. Now, the change in volume of liquid is defined as Ri minus Ro, which is just the rate of change of the volume. Think about it. If you have this initial amount and then you're adding stuff in while also taking stuff out, that net change right here is going to equal the rate of change of the volume. So I'd like to take your attention over here because we have a separable equation. So we can use this to actually find a function v of t. But actually, real quick, we're just going to redefine the rest of the stuff here. The concentration out is going to be the amount of salt in the tank divided by the amount of volume in the tank, which kind of makes sense. A concentration is a density, which is a mass over a volume, and it's thoroughly mixed. So at this point, when it's coming out, it's just going to be everything that's inside the tank divided by how much is in that tank. How much salt divided by how much volume, which is what we have right here. And then the change in concentration with respect to time is just going to be the concentration in times its rate that it's being pumped in minus the concentration out times its rate being pumped out. And I think that kind of makes sense if you just think about it for a little bit. And finally, we can plug in CO for this, and then we can rearrange, we can like add both sides, and then we get this term right here. That's our final equation, which we can use as an integration factor because we don't have any like constants or variables here. We just have a plain dx dt. We have a constant on this side, so we have it in a form that can be used with an integration factor. So now let's jump right into this problem. So dv dt equals Ri minus Ro. What I want to do is find a function v of t so we can find out what the concentration out may be. So first of all, I just want to plug in what we have given, which is Ri and Ro. So we can say dv dt equals 5 minus 4. And if you think about it, we have more being pumped in than being pumped out. So 5 minus 4 equals 1. So every single minute, we're going to gain 1 liter of mass. But just to further, just for good practice, let's just solve this separable equation. So we move over the dt, multiply both sides by dt, we cross it out, and we get dv equals 1 times dt. And then we'll integrate both sides, and we can see this as just a 1 right here. So 1 integrated with respect to dv is just v plus c, and then 1 integrated with respect to t is just t plus c. And then this plus c can just absorb that plus c, so we get v equals t plus c. And well, what is plus c? Remember, plus c is our like initial condition. So right here we have 100 liters of water at time equals 0. So v of 0 equals 100. And we just plug that in, and we get 100 equals 0 plus c. So c equals 100. Therefore, v of t equals t plus 100. Hopefully that all made sense. So now, as we move on, I'm actually going to start plugging in some stuff into this master equation, which is how we're going to find x of t. And note that you need x of t to find the concentration out. So we have v of t, we have Ro, we have Ci, we have Ri. So we have a lot of what we're missing. So let's just start adding stuff in. Dx dt plus, so right here, I'm just going to switch these around, and you'll see why I do that later, but they're both multiplied by, like on top, like they're both in the numerator, so you can just switch them around. But it's just so I can have a more convenient integration factor, just to put in integration factor form. So RO is actually just 4 over t plus 100, because that's v of t, and then times x of t, but we know it's in terms of t, so we can just write x for simplicity's sake, equals ci, which is 4, times ri, which is 5. So let's make some more room right here. I'm going to hurry up a little bit because I only have 4 minutes left, but so we get dx dt plus 4t plus 100 times x equals 20. And we have this in integration factor form, so we can find our integration factor as just e to the integral of this right here, 4 over t plus 100 dt. And with the 4, we can just move it on the outside because it's just a constant. So let's do that. So we got 4 times that. And integrating 1 over t plus 100 4 times with respect to dt, well, this in the denominator, degree of 1, we just know it's ln of t plus 100 times 4, and we still have this base e. And remember our logarithm rules. If we have a constant multiplied on the outside, we can just move it as an exponent on the inside. So we have e to the ln, absolute value of t plus 100, and all of that to the 4th power. And e to the ln, that cancels out, so we just have t plus 100 to the 4. That's our integration factor. So now we multiply everything by our integration factor, and when we do that, we'll have the power rule just end up on the left side. So we know that it's just going to be our integration factor times x of t, which we'll just say is x, but it's prime, its derivative, equals ci times ri, which is 4 times 5, which is 20, times our integration factor, which is t plus 100 to the 4th. Now we integrate both sides, and, well, we integrate this prime overall, so it's just going to be itself plus c. And then right here, this just works out to be 20 over 5, just a power rule. Only 1 degree equals 1 on the inside, so we don't need to do much use substitution. We can just do that in our head. And 20 over 5 is just 4. And we still have this plus c, and the other plus c absorbs it, so we divide by t plus 100 over 4. And we get x equals 4. This cancels out. And then we have c over t plus 100. So t plus 100 to the 1st degree plus c over t plus 100 to the 4th. And now we know x of 0 equals 0.